In this video, I'll be describing single slit interference. It's part of topic 9.2 in the IB Physics Syllabus, which means it's HL material only. Take a moment to read the success criteria for the video. Okay, one of the first things we need to realize for interference is that the waves have to be coherent. Now, this is really important. What that means is they're going to have the same wavelength, and they're going to be able to interfere using our principle of superposition. That means they're going to add vectorly where they are. Their displacements will add in a vector way. So a trough and a crest will then destructively interfere, and we wouldn't see any movement of the particles of the medium at that point. But if two crests would then interact, we get like a supercrest. And no, that's not a official word, supercrest and supertrough, but it tells you that the crest being created is going to be greater than the individual ones. So they've added together, constructively interfered. Now, we wouldn't get a consistent pattern if our sources weren't coherent. So a constant phase difference, so they're always going to be the same amount apart, and also with being the same wavelength. So let's take a look at the diagram here. So what we have is we have a wave coming forward, and it's coming towards this gap. So there's a single slit. Now, according to Huygens, and yes, I can't say his name quite right, all the points on a wavefront will act like a circular wave, and together they create a new wavefront. So when our wavefront comes along and reaches our gap here, we could assume that we have an infinite number of individual waves, circular waves, starting here. Now, as they move through, then they're going to interfere with each other, and it will be in all radial directions. So what I want to think about first of all is let's consider the wave that's going to be created here at number 5 and here at number 3. And what we're going to say is we know that they're going to interfere in such a way, some very far distance away, way up here somewhere, and it's going to be a position of our first minimum. So that would mean that they're going to destructively interfere. Now I've taken one from the very top and one from the very middle. And if I want those two to destructively interfere, that means one's going to have to travel half a wavelength longer than the other, so that when one arrives as a crest, the other will arrive as a trough. So in this case, since I'm pointing up in this direction, that means number 3 is going to travel a little bit farther than number 5 when they get to that point. How much farther? Well, that's where this triangle comes into play. So it's going to travel that distance farther. Now, I'm saying here as well that the angle that I'm pointed at from the center is going to be theta. And this is going to be true for every one wave at the top. So I said let's talk about 5 and 3. The exact same thing is going to happen with 4 and 2. So for every one wave in the top half, there'll be a bottom half wave that's going to just the same destructively interfere, and it's going to travel 1/2 wave longer. This is probably a good time to point out the difference between the words path difference and phase difference. Now these waves, remember, started off coherent because they're coming from the same wave front. But when they arrive at our screen where I'm going to see a minimum, I'm going to have a phase difference, in this case, of pi. That means one's going to be a peak and one's going to be a trough. Remember, one whole wave would be 2 pi, and this is half of that. So the waves are out of phase by pi. The reason why they're out of phase is number 3 has traveled farther than number 5. How much farther did it travel? It traveled half a wavelength. So if you're talking about an actual measurement in meters, you're talking about a path difference. If we're giving a value of where they are within the cycle, then we're talking about a phase difference. So here's a summary of all the things that I said. Light's going to be diffracted at the opening, and it'll be in all directions. And we're starting off by just thinking about ray 5 and ray 3, one from the top half and one from the bottom half. And we're going to be able to repeat this all along the slit. At that particular angle that I'm looking at, theta, I'm going to be looking at a minimum, a dark part, not a bright fringe, but the dark part where we're going to have destructive interference. That means that number 3 is going to travel lambda over 2 farther than number 5. If I wanted to talk about a constructive interference, I would have a different angle, and I would need a path difference of lambda. Now, hopefully you can realize that there will be different places that I can go, because I won't get just destructive interference with lambda over 2. If I had a greater angle, then number 3 might actually travel 3 lambda over 2, and I will get destructive interference again. We talk about this as being odd integer multiples of lambda over 2. So that's 1 lambda over 2, 3 lambda over 2, 5 lambda over 2, etc. Let's look at that little triangle in a little bit more detail. Now, we said that this distance here is going to be half of the width of the slit, and we're going to use B to stand for the width of the slit. We also said that this distance here needs to be lambda over 2. We also have this angle theta, but if I want to talk about it in the triangle, then that's actually this angle here. Let me quickly walk you through that if you don't see it right away. These two angles here add up to 90 degrees. Now, because this is a 90-degree triangle, this one and this one adds up to 90 degrees, which means then we have this being theta. So, let's use some trigonometry. What we have then is we have sine theta is going to be lambda over 2 divided by b over 2. Because compared to theta, lambda over 2 is my opposite side, and b over 2 is my hypotenuse. So sine is opposite over hypotenuse. Now, one other thing we're going to use with this, let me just cancel those out. That will simplify down to lambda over b. We also use something called small angle approximation. Our small angle approximation gives us that sine theta is about the same as theta, as long as we talk about theta being in radians. Now, when we do these kind of experiments, our value of b is going to be very small compared to the angle. So, for example, try it out right now in your calculator. Try a value of 0.1 radians. You're going to see that those values are almost the same. That means my equation can then be written as lambda over b equals theta. Really important in this section that you remember that in this case, for single slit diffraction, that theta is the first minimum. Now, I keep talking about this idea of a minimum. What do I really mean? So here's kind of a almost cartoony version of what we're talking about. So light comes and it's going to go against my single slit right here, and it's going to diffract as we go through. And here's an idea of what I'll see on my screen when I get this to land and be able to view it. Now, what this picture here is supposed to be is the intensity versus the angle. you can see that has a very big peak here. Think of it as this is the base. So here's my peak. And it's very high because I have a very large intensity here, and we call this our central minima. The first minimum that I was talking about would be right here in the center of this dark band. You can see I have no intensity. I go to the next one, and notice that the intensity here decreases. One really important thing to note about the pattern, and yes, you do have to know this pattern, is that this peak here is much less than the central one. And on a previous exam, you had to make sure you drew this at least less than 20%. It is even farther than that, but a general rule of thumb, if you have this as being 10 tall, make this around 1 tall, okay? What you're going to see is also symmetry. So whatever angle was up here is going to be the same down below, because instead of me drawing my rays up in this direction, 5 and 3, I could have easily have drawn them this direction. And again, with theta lambda over b, it doesn't say, above or below our central axes. So one other thing I want to point out is notice you have a central wide band. Okay, because of that, our equation theta equals lambda over b gives the distance for a first minimum. That would be here on both sides. If I had 3 lambda over b, remember we could have had it as not just lambda over 2, but it could have been 3 lambda over 2, I would get to this point, and so forth. Okay, so what other things can we get from this pattern? Well, if I change the wavelength, and if you remember, red has a larger wavelength than blue, or in this case we could talk about green. What does that do? Well, if my wavelength is larger, I will get a larger value of theta. So that means the distance between the theta equals 0 up to where I'm predicting my minimum occurs is going to be greater in red than it is in green. Okay, so let me give you some other information about this. Typically our value of B is going to be in the neighborhood of up to 1 millimeter. Okay, so it's going to be very small. Our D, capital D, that's the distance between our slit and the screen where I'm seeing these bright and dark bands. That's going to be more like, 2 to 4 meters. So much, much larger. And that's why we know, first of all, this picture is not to scale. And theta is going to be very tiny. Also, the distance from the center to the first minimum, I've labeled here as x. We're still going to be talking about, maybe up to 1 centimeter here, depending on what we're using for wavelength. So we already have our value from the single slit diffraction. Theta is lambda over b. I want to show you one other measurement that we do use quite a bit. If you look at here now with this diagram, now I can say that with theta, look, I have opposite and adjacent. Now that would be tan theta is going to be x over capital D. Now, since we have, again, such small angle that we're using, as long as we are in radians, tan theta is basically the same as sine theta. Because this is so small, what we're saying is that the opposite side is basically the same length as the hypotenuse. That is, this length and this length are going to be very similar. So similar that, for the number of significant figures we have, we can say they're about the same. So that's going to be about the same as x over d. And again, since we are dealing with small angle approximation, that's the same as theta is x over d. So I could put these two equations together. So I'd have lambda over b is basically equal to x over d. And sometimes we'll use that to answer our questions. So let's set up this question. Light from the laser is used to form a single slit diffraction pattern. The width of the slit is 0.1 millimeters. And the screen is placed 3 meters from the slit. And it says that the width of the central maximum is 2.6 centimeters. Now, one of the things I want to point out about this is that's the width of the central maximum. That means from both sides of this dotted line that I have down the middle. So if I want to measure x, just the distance from the center to the first minimum, that's actually going to be 1.3 centimeters. Now, one thing I want to point out here is all of these are in different units. The easiest thing to do is to right away put in your multipliers to make sure they're all into meters. Now, let's go back to our equation. Yes, we have theta is lambda over b, and in this case, theta is going to be the same as x over big D, and if I move that around for lambda and put in my numbers, and that's going to give us 4.3 times 10 to the minus 7 meters, which is 430 nanometers. And just a quick check with that, that would give us visible light. So please take a moment to reread the success criteria, and hopefully now you can agree to all of those statements.